What about esters? We've talked about esters quite a bit already. They're actually very widespread in biological systems anyway. They're typically responsible for pleasant smells of fruits and flowers. So methylbutanoate, it is a ester that gives pineapple scent. Here's isopentyl acetate that we talked about. You most likely made that first semester. That's banana oil. Here's a fat. It has a 3-carbon chain to it, and then off of each of those 3 carbons is an O, C double bond O, R group. So if R are long chains, that's how we have fats and oils. So those can be cleaved to make fatty acids, H, O, C double bond O, R. If that's a long chain, that's just carboxylic acid. But if R is a long chain, it's a fatty acid. Okay. If we do it under basic conditions, here's water, let's call it H3O+. We can get fatty acids under basic conditions. As we'll see in just a moment here, we can get carboxylates, O-, C double bond O, R, and that is a soap. As we'll see in our lab project that we've been doing, if we mix this with methanol and some sort of acid catalyst, we get CH3O, a different ester, C double bond O, R, which we use for biodiesel. Okay. In each case, those R groups are long chains. So free fatty acids are just carboxylic acid. A soap is a carboxylate salt of a free fatty acid. Biodiesel is a methyl ester of a fatty acid. Also commonly used industrially are phthalates. That name comes from the fact that benzene with C double bond O, OH on 2 adjacent carbons is called phthalic, PHTHALIC acid. Okay, so the esters of phthalic acids are called phthalates. So here is dibutyl phthalate, and those are used as plasticizers. So without them, plastics would be very brittle, very hard. They would just shatter instead of bending and being flexible. These phthalate molecules help to make the properties of plastics more reasonable to their use, but that's why you have to be careful when you're microwaving things in plastic containers, because these phthalates can leach back out into your food, and they're not good for you to consume. So let's talk about ways we can make esters. We already showed you the methods for making esters out of carboxylic acids, right? By deprotonating an acid and making a carboxylate, then doing SN2 reaction with like a primary alkyl halide, we can make an ester, but that's limited to primary alkyl halides. If we do an acid catalyzed reaction with an alcohol, that's the Fischer esterification that we talked about, but that's limited to simple alcohols because we need such an excess of ROH, and it has to be liquid, right, since they need to mix together well. So the most general way to make an ester is, if I have a carboxylic acid, first make it into an acid chloride that activates it for nucleophilic substitution, and then with any alcohol, right, this alcohol is the nucleophile while the chloride is the leaving group. And that's a very general method. It's similar to formation of anhydrides before, except we don't need an alkoxide. The acid halide is a powerful enough electrophile to accept a neutral alcohol, but we need to have pyridine around. We need to have some sort of base like that around to deprotonate the resulting alcohol and sop up the HCl that's produced as a result. So that method is very general. Any ester can be made with that method. Let's talk about esters. First of all, FYI, a lactone is a cyclic ester. So here's a 6-membered ring. It has a C double bond O and an O in the ring, right? So that's a lactone. All of these ester reactions work equally well with the cyclic esters. So let's talk about ester hydrolysis. We can use acid or base catalyst and essentially react water with an ester. So this OR is the leaving group, water is the nucleophile. So it replaces OR with an OH to make an acid. Right? That's our carboxylic acid. Plus, the leaving group becomes a free alcohol. And when you're investigating these, view OR and the OH, right, from the water. Right? Water if it's acid catalyzed, hydroxide if it's base catalyzed. So view OR and OH as group units that are exchanged. So if we look carefully at, for instance, isotope studies, it tells us exactly which oxygen is which, right? So it shows us that the CO single bond next to the ester carbonyl is the one that's broken in ester hydrolysis, right? So if we used an isotopically labeled oxygen in the ester, right? So if we had OCH2CH3 be radioactive O isotope, we would see that same O, that radioactive O, in the alcohol product. That O is not retained in the carboxylic acid. So that's why I said to view OR and OH as two groups that are swapped in ester hydrolysis. So let's look at the mechanisms of this. Basic hydrolysis of esters is called saponification because it produces a soap from animal fat. That's one of its key functions. So let's take a look at what happens. If I have an ester with hydroxide, that's our base. Hydroxide is the nucleophile. We have a tetrahedral intermediate where OR is the leaving group. Initially, that makes a carboxylic acid with a alkoxide that has been kicked out, but there's a very fast proton transfer, okay, because carboxylic acids are more acidic than alcohols, right? pKa of 5, for the alcohol, pKa of 16. So what's going to be favored, since the carboxylic acid is a stronger acid, it will donate its proton to the alkoxide. So we end up with a carboxylate salt. And if we just stop at that state, we have a soap, provided that our R is a long chain. Okay. Otherwise, if it's just any old carboxylate salt, we can react aqueous acid with it to make the free carboxylic acid. Right? So, in general, an ester reacting with base can give us a carboxylate salt, but then I protonate it to make a carboxylic acid. If I do this same reaction under acidic conditions, what happens is that esters, they can only be attacked by neutral nucleophiles like water if they're first protonated. So same old rule, we have a carbonyl reaction with acid catalyst. The first thing that happens is the carbonyl is protonated. That activates the carbonyl for nucleophilic attack by just regular old water. So here's the water that's added. We now have an alcohol. Here is the proton transfer that occurs, right, from the extra H that was on the water that just attacked to protonating the OR group, right? That makes the OR group into a better leaving group. Okay? If we just left it the way it was, our protonated water is the leaving group. And if that got kicked out, we'd be right where we started with. Okay? So in order to advance the reaction forward, a proton transfer has to go onto the OR group, which protonates it. Then, by removal of the hydrogen off of one of the OHs, we're able to bring electrons down and kick off the leaving group. Okay? So This step here is a little bit of an abbreviation more than we have seen before. If you'd like to do this in 2 steps, if it's a little clearer for you, you could have this be an intermediate, a protonated carbonyl. Like that, which then may get deprotonated. Okay. But if you're comfortable removing this proton and essentially doing an elimination reaction, which regenerates the catalytic acid, kicks out a neutral alcohol from that same process. We can convert an ester into an amide, but this reaction is not necessarily very common since, again, amides are going to be best prepared from acid chlorides, but esters technically are more reactive than amides are, so reaction of just a plain old amine should be able to displace the leaving group, making an amide. That reaction probably will take pretty harsh conditions, and it won't work very well, but it's definitely possible. If we talk about reducing esters, again, if we use lithium aluminum hydride, that's powerful enough that it'll add twice to the ester. So if we look down at our mechanism here, hydride will react with the ester, it'll make an alkoxide and kick out OR minus. Here's our aldehyde intermediate. But because I have all this extra hydride around, another equivalent of hydride will add again to the carbonyl, and then protonation will give us our alcohol. So take a very careful look at these substances here. When you're doing lithium aluminum hydride with an ester, always consider the OR group to be a leaving group. So I can draw the aldehyde intermediate here, CH3, CH2, CH double bond, CH, C double bond OH. Another equivalent of hydride, and then here, let's do this correctly. First hydride, then acid for workup to protonate it. Okay? Because hydride adds right here, it gives us our other H. Those are the 2 H's right there that are added. The acidic workup protonates an alkoxide from that. This one right here, starting with a lactone, this is a little trickier. You have to be a little careful because our leaving group is really part of the same molecule. So you can just sort of consider it like that. Our aldehyde intermediate, believe it or not, looks like this. Let's see here. Let's do C double bond O H, and then O minus. Okay, because then the second equivalent of hydride will add to the aldehyde there, making the primary alcohol over here on the end. This other OH came from the O that was originally part of the leaving group that got protonated with the acidic workup. So with an ester, if you have just a normal open ester, you'll get the alcohol that came from your actual ester as well as an alcohol that was the leaving group. Okay, so be careful to draw both of those. If you have a lactone, which is a cyclic ester, you'll have just one molecule, but it'll have 2 OHs. It'll be a diol. If we do want that aldehyde intermediate, if we want to stop at that aldehyde and not go any further than that, we can use a bulky hydride reagent like diisobutyl aluminum hydride. We had mentioned that before as a way of producing aldehydes from esters. So DIBAH or dibol or dibol H as I know it most commonly. Our book though calls it DIBAH diba or something like that. That only reacts with carbonyls like esters that are electron rich. Okay? So diabod doesn't work with acid chlorides or really anything else like that. So this is sort of particular to esters where we can stop at the aldehyde stage like that. If we want to do a Grignard reagent, Grignard reagents will add twice, just like lithium aluminum hydride. So here's our methyl benzoate. It's an ester. I've got two equivalents of phenyl Grignard. So if I want to draw the product of the first addition, we're going to have pH, C double bond O, pH. We're going to have benzophenone as a ketone intermediate. And then the other equivalent of Grignard reagent followed by acidic workup will give us a tertiary alcohol as a product. Be careful here. The OCH3 was our leaving group once again, right? The Grignard added to it. It kicked off the OCH3, so we have addition of one R group regenerating the ketone, right? So the second equivalent of Grignard reagent can add to the carbonyl. So we cannot isolate the ketone intermediate. Okay? If we want to do a Grignard reaction where we only add one R group and end up with a ketone, we have to use an acid halide with a Gilman reagent. Remember, Gilman reagents are weak nucleophiles. They can only add to a very strong electrophile, like an acid halide. Okay? Gilman reagent won't react at all with an ester. Ester is not a powerful enough electrophile. This carbon here isn't plus enough for a Gilman reagent.